Did you know that you can use plasma to control the flow over an object? One of the most common ways is to prevent boundary layer separation. So the way it works is that a boundary layer will separate when it effectively loses too much velocity in the lower region near the wall, and the flow will reverse and lift off. And there are many ways to delay this phenomenon, with the plasma method being one of the most common ways. So we introduce plasma in the near wall region, and that can do a couple of things. So we can have a couple of different ways that it can prevent boundary layer separation. The first way is that it turbulates the boundary layer, which increases the velocity in the near wall region. And that means that the boundary layer can travel farther downstream before decelerating to the point where it separates. And this can be done through the plasma creating a force on the boundary layer, so it actually accelerates it through the plasma itself, which we'll cover later in this podcast. Another way that plasma can be used to prevent boundary layer separation is through creating vortices, which then mix the fast-moving flow higher up in the boundary layer and even in the free stream flow into the lower parts of the boundary layer near the wall. That then re-energizes it, and there's something called a momentum exchange. So with this approach, the plasma is effectively just vortex generators. So how do we create this plasma? So one of the most common ways is to use something called a surface dielectric barrier discharge. So what is that? Well, we have two electrodes as shown in figure 1 here. So let me scroll up here. And they are sandwiched between, and in between there is dielectric material sandwiched in between. So let me zoom in here. So we have one electrode here, one electrode up here. In between is this dielectric material. So what is a dielectric material? So this is a material effectively with just a really high resistance. So when you apply current to it, the electricity won't flow through it. It insulates it. But there's also one more important property that makes it a dielectric material and not just a really good insulator. So that property is that when you apply a voltage across the material, so in this case you apply it across the two electrodes that are sandwiching this material, the material becomes polarized. And that means that at the atomic level, the electrons around the nucleus shift a little so that one side of the entire atom is now positive and one side is now negative. So there's that net difference there. So all dielectric materials are really good insulators, but not all really good insulators are dielectric, because some insulators don't become polarized. And that is a very important property that we need to produce plasma. So one really common example of a dielectric material readily available in the engineering world is Kapton tape. And you can buy it for like a few bucks for a roll. So when you have this dielectric material sandwiched between these two electrodes, you then put this ensemble onto the surface with one electrode face down and covered by the Kapton tape, and the other electrode is exposed to the air. So then you apply an AC voltage to this ensemble through the electrodes, and a jet of plasma that goes from the exposed electrode to the direction of the covered electrode occurs. That can then produce a force on the surrounding air and do what we were talking about earlier, where that is either to act directly on the air and accelerate it directly through this force on this air, or create vortices and then mix different regions of the free stream flow or the boundary layer and free stream flow together. So either way, this dielectric barrier discharge, which will term from now on DBD, prevents, or at least at the very least delays stall. So that is how a DBD works. And DBDs fall into the active flow control device category. So the alternative to that is being a passive flow control device. So the reason why this is an active flow control device is because it uses energy. A passive flow control device is one that doesn't. So an example of a passive flow control device is a typical vortex generator, which is just like literally like a prism that you put onto the surface, or it can even be like a golf ball, like half a sphere or whatever. That's just an object that you put on there. That is a passive flow control device because there's no energy being used in there. And you might have noted that I used this example, a vortex generator, and that is because often we can have the same general flow control device as a passive version or an active version. Not always, but sometimes. And in this case, DBDs and physical vortex generators can do both the same thing, create vortices that manipulate the boundary layer, but one uses energy while the other one doesn't. So why would you want to use an active flow control device or a passive flow control device if you can do the same thing kind of thing? Well, there are benefits and detriments to each one. One of the major benefits of an active flow control device like a DBD is that it uses that's more effective than a passive flow control device. So if you want to make vortices, for example, you can make stronger vortices. You can manipulate where they are and when you turn them on and when you turn them off. On passive flow control devices, they don't use any energy, but they usually are not as effective. So sometimes the passive flow control device, while it might not be as effective, uses no energy. So when you assess the entire system, you might find that the passive flow control device is actually better because it yields an overall more efficient result. On the other hand, sometimes the active flow control devices produce far greater benefits than the amount of energy that are required to run them. So overall, they are better options. So you have to assess the entire system together to see which one is better. And there are other differences between them. For example, active flow control devices, as I mentioned, you can toggle them on and off. Passive flow control devices, you can't really do that. Active flow control devices, they are usually more sensitive. They're usually easier to break. Passive flow control devices are usually much more robust. So there are some trade-offs there. And to this end, we reach the topic of today's podcast, and that is, how do different voltages applied to a DBD affect its performance? So does applying a greater voltage result in a more effective DBD? Is there a linear relationship, and does this relationship hold constant when you move the electrodes closer together or farther apart? So this DBD here, you can change how thick this Kapton tape is and where these electrodes are placed. And to answer these questions, we are looking at a paper called, if I scroll up and zoom out a bit, Effects of Surface Dielectric Barrier Discharge on Aerodynamic Characteristics of a Train. So this bad boy is open access, and you can find it in the link below. And so to answer these questions, these chicos and chicas looked at a DBD on a train. And the reason why they wanted to look at a train is because they like trains. And you can actually use DBDs on trains to control flow separation as well, because there are certain points on a train which the flow will separate over. And believe it or not, but trains are very important transport vehicles. Like when you go on engineering or whatever, and you learn about airplanes, cars, they're all really cool because I use them every day. But you don't ever really hear about like these heavy vehicles like trains and even semi-trailers and that, because they're not that exciting, but they do the bulk of our transport work, and they are far more important to our society than what we think. And like if you look at how much energy is used and like inefficiencies and stuff like that, the transport industry is actually like dominates the all transport industry in terms of trains and shipping and heavy duty vehicles. So they are very important, including trains. And they did this via experiments, this research, which is really cool. So figure 2, we see where they put these DBDs on trains. So let's scroll down to that one and zoom in a little bit. So in the top figure, we see that they put it just at the end of the train's head and at the start of the compartment bit, so that interface between the two. And on the bottom figure, it shows an electrode at the back of the train. So this train is, this isn't actually like a proper high-speed train. We have two, like the tail is sleek like the nose. This one's more like just you have the front compartment where you have the train front and like the nose, and then it goes to the cabin and then the abrupt stop of the cabin. And then you have a flat surface at the rear there. So it isn't the end of the train, really. It's more like the end of one compartment of a train, and then you can add more compartments to the train after that. Now, I'm a little surprised that they would opt to put a DBD here, because this is a completely flat surface, and I wouldn't expect there to be any chance of keeping the bandulate attached here. But I don't know. Maybe there is a surprise here, and the DBD is working in a different way. I actually do know what they'll find, but I'm trying to make it a surprise for you. So we'll see at the end. So anyway, the DBD has its electrodes made of copper, which is good, and the dielectric material between them was polymethyl methacrylate. Or PMMA to its friends. So the power supplies could range from 0 volts to 30,000 volts, which if you touched that, you'd know you're alive, and unless your heart stopped, in which case you'd be dead. But anyway, that might be a bad analogy. Anyway, the AC power could be toggled anywhere from 5 Hertz to 20,000 Hertz, which means that you can literally run this DBD at different frequencies, what you're going to be making plasma at. But they decided to fix it at 9,000 Hertz for this entire experiment, so that's a good choice. They measured the temperature of the discharge zone with an infrared imager, which is cool because plasma is usually really hot, and I wonder how hot it is here, and if that would affect the train or whatever surface you'd have it on, because if it starts melting away the train, that's not a great idea. Now, let's say that they used a glass pressure probe to measure the induced flow velocity, so the velocity that's being induced by this DBD. And to be perfectly honest, I don't really understand what they mean by this using a glass pressure probe, because they don't really give any details about how many holes are in the probe or the geometry of the probe. So is it a kill probe or a pitot probe or a ram probe? I don't know. I also don't know how it was oriented to the flow. I mean, They say that they used it to measure the induced flow's velocity, but to do that, you need to align it with the flow usually, otherwise you'll get errors, and you don't really know exactly the direction of the flow. So maybe they used a keel probe, which is far less sensitive to the angle, or maybe even a multi-hole pressure probe. So I don't know exactly what they mean here, but they just say that they used a glass pressure probe of some description to measure the velocity of the induced flow. And we'll see the results later on. So one cool thing they did was that they used smoke flow vis to see the plasma and the effects of the DBD on the flow itself. And one thing to note is that for these experiments, they used a scale train of a 1 to 250 scale model. I'm not sure how that will affect the results and how transferable the results are to real life. And the reason I say that is because if you have a 1 to 250 scale train, you can't really run it at the speed required to reach similitude. So if you had a train of, like, let's say it's going at 10 meters per second, the full scale train, if you go to a 1 to 250 scale model, you then need to run it at 250 times that speed, which obviously you're going to get compressible effects. That's not going to work. And in fact here, they ran the wind tunnel at 7 meters per second, which gave a Reynolds number of 33,973 based on the train's 10 centimeter length. Now that presents a potential problem because a Reynolds number of 33,973 is prime territory for laminar flow. And in this zone, the DBD will stand the greatest chance of making a positive impact here. If you were to bump, and that is because if you have a slow moving flow, it's very laminar. It means the flow near the surface is very slow, which means that it's going to separate much more easily. So the DBD is going to have a much greater effect on this region than if you had like a 10 million Reynolds number, where the flow will now almost certainly be turbulent, and the chances of the DBD having a positive impact will go down because the boundary layer will already have quite a high velocity near the wall. And secondly, the length required to decelerate the boundary layer to the point where the DBD will have a significant effect will be different. So there's a potential potential for there to be an apples to oranges comparison here. I mean, they are still both trains, so maybe it's more like apples to apple flavored Jello or some other kind of apple product. But that doesn't mean that this research is useless because it still gives some insight into how DBDs will affect A geometry in general at this general Reynolds number. And one thing that isn't often talked about is how to overcome the limitation of different Reynolds numbers based on a boundary layer. So if you were to like go into a lecture or whatever, or you read a book or whatever, or a paper, people often try to get the exact same Reynolds number, and when they can't, they go, oh, well, that's all we can really do. Well, in fact, just because you don't have the right Reynolds number doesn't mean that you're out of options necessarily. And if you go to our YouTube video, Aero Fundamentals number 2, Reynolds number explained, we go through the limitations of the Reynolds number, and it's a really good video, and I bet you haven't heard some of the things that we're going through in that video, so check that out. But anyway, why this matters is because let's say we have a Reynolds number of 33,973, and in real life, it should be 1 million. Okay, that is quite a big difference, but there are some things you can do to get the flow physics closer, despite having such a large chasm between the two Reynolds numbers. The first thing you can do is to make the surface rougher of your object, of your model, to not your real life training, but your experimental model. Making the surface rougher will introduce more turbulence, and while it won't necessarily make the flow behave exactly as if the Reynolds number was 1 million, it will bring it significantly closer. The boundary layers will be much more similar, hence the effects of the DBDs will be more realistic. Another thing you can do, despite the large differences in the Reynolds number, is to make the free stream flow have a higher turbulence intensity. That will result in more perturbations on the boundary layer and cause it to transition at a lower Reynolds number. Now, 33,973 is very low for a boundary layer to transition to turbulence, but with a high turbulence intensity level and greater surface roughness, it is doable. It can even maybe potentially trip the boundary layer. So just because the Reynolds number is different doesn't mean that your hands are tied. You still have other options. So that's a little trick when you do experiments, if you have the right technology to measure the boundary layer profiles, and that you can play around with the surface roughness, turbulence intensity level, trips to get a different Reynolds number boundary layer effectively. Anyway, let's move on. One other thing that I would have liked to have seen in this paper is the blockage ratio and even the turbulence intensity level of the free stream flow. These pieces of information about the wind tunnel are very important, but they don't give them, so I don't know if the train was taking up a lot of the cross-sectional area or not, and the resulting difference in the flow physics. That would have been good to see, but we don't have it here, so anyway, let's move on to the results. So in figure 4, as we come down here, let me zoom in a little bit. Here we go. So in figure 4, we see how much power is consumed based on the applied voltage to the DBD. As I mentioned, you can put the DBD on this one between 0 volts and 30,000 volts. It's interesting to note that as the voltage increases that you apply to the DBD, the power consumption also increases, but not in a linear way. It seems to follow a quartic, in other words, a fourth order polynomial with the third order, second order, and first order terms having a 0 coefficient effectively. That's what they're saying here. It seems to be just proportional to the voltage to the power of 4. So if you're going to apply more voltage, what this means is that you'd hope that it would have a much greater effect than just a linear increase. Otherwise, efficiency will drop because you're using more power just for a linear increase as opposed to like a lot greater increase. So they say that this non-linear relationship is because of the capacitance of the dielectric material and the impedance of the plasma change with changing voltage. So if you increase the voltage, these changes result in having to use more power to produce plasma. Now, in figure 6, they show the temperature of the DBD when powered on, and this is really cool. So remember that it produces plasma, this DBD, and some forms of plasma in common life are fires and even the sun. So you might expect the temperature to be really hot because that's what fires are, that's what the sun is. But that's not really the case here. So the highest temperature we see, if we scroll down here, across the different conditions of the voltage that we're using, so 27,000 volts is really the highest temperature that we'll see here. It gives you a maximum of 85 degrees Celsius around this DBD. That's it. And that might be enough to burn you, but nowhere near enough to melt metals. So I'm a little surprised at that because I thought that the temperature might be higher. And in fact, if we look at the lower voltage of 21,000 volts, which is still enough to send you into the next world if you touch it, the maximum temperature is still only about 60 degrees Celsius. And at that temperature, I'm not even sure if it would be high enough to burn you. I'm not sure what the conductance is there. But 60 degrees, even in metal, is borderline enough to burn you. So I don't even think you'd even get a burnout of this potentially. So the temperature is quite cool here. And as you go only a few millimeters away from the DBD, the temperature drops to only 30 degrees, which is really cool when you think about it. Like, so unless you touch this DBD, chances are that you probably won't even burn yourself just by putting your hand around the plasma. And in fact, at these kinds of temperatures, I wonder if you could briefly hold the plasma in your hand and like throw it around. That would be really cool. Anyway, one question that arises is how does the distance between the two electrodes affect the velocity of the fluid around the DBD? Because as we mentioned, there are two different ways that the DBD can really affect the flow. One was literally producing a direct force on the flow. The second way is by like producing vortices that then interact with the flow. This first way is what we're looking at here, which you're literally producing plasma, and then this produces a force on the flow, which we'll cover in a second. So in figure 7, we see the results of widening the gap between the two electrodes from about 5 millimeters to 50 millimeters, and what the effects are on the velocity that it induces in the flow. So generally, we see a sweet spot, and we also see that as the gap reduces, the velocity of the fluid around the electrode, around this DBD, increases. But that trend only holds down to about 10 millimeter gap, from 50 millimeters down to 10 millimeters. And then when you go to 5 millimeters, the velocity drops a little bit. So what this means is that there's a sweet spot where the DBD is producing the best effects. So to give you an idea of some of the velocities we're talking about, for a voltage of 21,000 volts with a 50 millimeter gap between the electrodes, the flow's velocity is only about 0.7 meters per second, so down here. But if the gap between the electrodes is dropped to 10 millimeters, the velocity increases to about 3.5 meters per second. So it's quite fast now, that's 10 k's per hour. But then if we drop it to 5 millimeters, this gap, the velocity drops to just under 3 meters per second. So there seems to be a global maximum here for this velocity of the flow, that this DBD will accelerate. And the reason for this trend is explained by the authors as the charged particles around the DBD get accelerated because of the electric field. So you have these ionized particles that are exposed to this electric field. So they go from like positive to negative or negative to positive, and hence they gain kinetic energy. They accelerate and gain kinetic energy. The air around the DBD that isn't ionized, so just regular free stream flow, will get hit by these fast moving particles now, and hence the additional air gets entrained. That's how we produce a direct force on this air. The air that we've accelerated is now bombarding the other air and taking it along for the ride. Now, if this gap is too small, the transfer of kinetic energy through entrainment is less effective. Increasing the gap makes these collisions more numerous, and the entrainment process becomes more effective. And this is why when we have a 10mm gap, that's better at producing a higher velocity than a smaller gap. And actually, I think that while the researchers here said the surrounding air gains velocity through collisions of the fast-moving fluid, I also think that perhaps there is some kind of shearing going on that might also help accelerate the flow. So you have the fast-moving flow from the plasma, and that's like directly in contact with the free stream flow perhaps, and that's also dragging along as well. So I think it's not just because of the collisions, but also the shear that we're getting that accelerates the flow around the plasma. Anyway, as the gap increases, these collisions become more effective, but as you increase the gap, the strength of the electric field drops. So the charged particles won't accelerate as much, hence they don't have as much kinetic energy, and won't impart that kinetic energy into the surrounding air. That's why the surrounding air drops in velocity. So that's why there is this sweet spot. The distance is perfect, is a perfect combination between allowing more effective collisions between the ionized air and the fast-moving air, and the slow-moving air of the surroundings, and the electric field being strong enough to do that. Now this sweet spot was fairly constant with changing voltage. The best distance was around 10mm for 21, 24, and 27,000 volts. So in figure 7, we see the induced velocity of the surrounding air, and I guess also with the ionized air, so a mixture here. And I think this is what they were talking about using that glass pressure probe to measure the velocity of, which I still don't know what they used. Anyway, it shows how this velocity changed with changing voltage. So in other words, if you put more voltage into the DBD, will the velocity of the air around this DBD increase or not? Who knows? We know now. We have this graph here. So anyway, as the voltage increased, the velocity of the surrounding air increased as well. And this makes sense because a greater voltage means that the electric field will be stronger, and that will accelerate the ionized particles more. Hence, these particles will have more kinetic energy when they hit the surrounding flow, and thereby impart more kinetic energy to them. So that results in a greater velocity. And I find this graph quite interesting. So it shows that yes, increasing the voltage does increase the velocity, but it's not linear. In fact, it peters off a little bit as we get to higher voltages. I mean, the slope reduces a little as you increase the voltage. So that means that there will probably be a point where increasing the voltage further won't increase the velocity anymore, at least if it follows this trend still. One thing I should mention is that I really like that they have uncertainty bars on their figures, this figure, all these other figures. This is quite rare, but a really good practice because no matter what research you're doing, you're going to have uncertainty in your results. And when you just make a graph or give values and don't specify the uncertainty, it really doesn't tell us that much because we can't tell if the trends are true or if they're just within the uncertainty of the measured values. So I think these authors did a really good job adding these uncertainty bars here. So anyway, let's move on to figure 9, where we see some flow viz showing literally how DBDs work. So in these figures, we can see on the left here, there's some smoke going up at the start of the DBD, like 6 or 7 centimeters away from the DBD. So the DBD then extends like around 15 centimeters along the ground, perpendicular to this smoke. So it's like sort of forms a right angle here. So the smoke is quite far away from the DBD in general. Amazingly, as you turn on the voltage, so this figure here and this figure here, the smoke still gets pulled in from being so far away at 21 kilovolts. Pretty much all the smoke that was originally going up gets pulled into being just over the DBD. And I'm really impressed with how effective this DBD is at pulling flow from really far away over it and accelerating it. It's really quite amazing just how effective it is. It's encompassing like a huge region. Then when the voltage gets increased to 27 kilovolts, there is a lot more smoke being blown around. So it's really accelerating this fluid a lot more here. So just a 30% increase in voltage results in the surrounding flow getting manipulated a lot more, and this DBD is really effective. So let's move on to how this DBD affected the flow over the train. So in figure 10, we see some drawings on how it works, at least some conceptual ideas. And this is a very expected mechanism. So for a curved surface, like where the train's nose meets the rest of the cabin, without the DBD, the flow will separate because it doesn't have enough energy to stay attached. The boundary layer loses steam and then it reverses and lifts off. And that increases the drag and pressure drag. But when you put the DBD on, the separation is suppressed until much later because the flow near the wall is much faster as expected. In figure 11, we see the smoke flow vis over the front of the train without and with the DBDs at different voltages. So we have 0 volts here, 21,000, 24, and 27,000 volts as we go down. So I'll zoom out a little bit actually so we can see all of them. And I can't really see much of a difference between these figures, where the flow is going too much. I think that maybe there's too much smoke in the background to get a clear picture, but the authors say that when the DBD is on, the smoke is closer to the train, indicating more attached flow and hence less pressure drag and total drag. That definitely makes sense, but I can't really tell that from the pictures. I can't really tell anything from the pictures. I mean, the theory makes sense, so I guess that is what is happening. Anyway, what about the back of the train? Because we know that this is kind of expected, that the boundary layer will get manipulated by the DBD. What about when we had the back of the train where we had the DBD there, but there's no real boundary layer to manipulate? It's already separated. So going on to figure 12, we see the effects of having a DBD on the rear face of the train on the aerodynamics. And it is very clear that when it is on this DBD, the flow gets pulled down behind the train and into the wake to make this wake smaller. So without it, you can see it just shoots straight over and it's pretty horizontal. As you increase the voltage, it becomes more and more vertical. It just comes down. And this is really cool because it is kind of just a brute force mechanism. It's really not a sophisticated aerodynamic phenomenon. It's not like you're manipulating the boundary layer, changing it to turbulent. You're literally just pulling the wake down through entrainment to reduce the train's drag. And we see that the greater the voltage, the more this happens. So we have just seen that DBDs are also great for flat rear surfaces. And that is an important point in this paper because remember how we were saying that the Reynolds number looked in this paper was 30,973, and that was way off what you'd get in real life of maybe like 5 million or even higher. Well, that mechanism that the DBD induced at the front of the train, where it re-energized the flow, might not be that applicable at higher Reynolds numbers. I mean, sure, it might help a little, but the flow is already traveling really fast, so how effective the DBD would be is a little unknown. But the way the DBD affects the flow at the rear of the train, that has really nothing to do with the Reynolds number. The edge there at the back is sharp, so no matter what Reynolds number you have, that's going to be separating. So it isn't really a boundary layer thing, but just a crude way of forcing air into a different direction. So that effect will definitely still be applicable at higher Reynolds numbers. So you might need larger DBDs or higher voltages, but the same mechanism will definitely work, which means that when you put these DBDs onto large trains, you still will be able to reduce the drag of the train by reducing the wake size, reducing that pressure drag. So that's really cool. And with that, we come to the end of this podcast. I hope you liked it. And if you did, make sure to like it and click the subscribe button or follow button, whichever platform you're on. And if you want to learn how to do OpenFrame, which is a completely free and really powerful CFD software, take our course in the link below. You'll also find other CFD courses there as well. And did you know that most research experiments have a 2 to 4% error in them? The reason why is because most researchers don't measure the density of air in the wind tunnels when they're doing their experiments. And the density of air changes throughout the day by 2 to 4%. It changes even more between days, weeks, months, and seasons. So to get rid of this error, we made a really accurate instrument called the Atmosphere Hawk, which measures the density of air and gives it to either straight to your computer, so you can time it, like you can make it talk with your computer, or on a screen, or both. And if you want to get rid of the error in your experiments, get one of those in the link below. And that is all for this time, and I'll see you next episode. Peace, amigos.